lots of questions. The discussion is kind of encouraged. Yeah, so with this, I don't want to wait any further. I'm looking forward to your talk. I leave the stage, the virtual stage, to Professor Mian. Looking forward to your talk. Thanks for giving the colloquium today to us.
Thank you, Peter. Thank you, everyone. It's a pleasure to be with you here. And I wanted to introduce the Physicists Coalition for Nuclear Threat Reduction that Peter mentioned, and then jump into my talk. And as Peter said, please do feel free to interrupt and ask questions. So the topic of the talk today is dismantling the nuclear doomsday machine. And what I propose to do is to explain to you why there is a nuclear doomsday machine, how we got to it, and what is the current situation with regard to this threat that nuclear weapons pose to humankind, and then conclude by talking about some of the different initiatives that are being taken to try and help reduce the current nuclear threat, and the role that physicists have played in this story from the very beginning up to today, and ending with work that we're trying to start with our Physicists Coalition for Nuclear Threat Reduction. And as Peter mentioned, there will be a discussion afterwards about how to become involved. So let me jump in. There is an organization that is associated with nuclear weapons almost from its very founding, the Bulletin of the Atomic Scientists. And the name tells you something already, because the idea of an atomic scientist seems old-fashioned now. We talk about nuclear physics, but some of the scientists who were responsible for the first ever development of nuclear weapons, what was then called the atomic bomb, and the atomic scientists, set up an organization soon after the first nuclear weapons were made and used to explain to other scientists and to everyone else the danger of nuclear weapons. And so they came up with the idea of the Doomsday clock, which was a way to indicate how far humankind is from catastrophic use of nuclear weapons, of nuclear war. And so every year, this clock is reset by a group of scientists that try and assess the current state of the global nuclear threat, which has now been expanded to include other sources of threat also. But the clock was just reset in January of this year, and it is set now at 100 seconds to midnight, where midnight represents a catastrophe for humankind. And so what I'm going to try and do is explain how we got to a situation where people believe that we are so close to doomsday. A key part of this has to do with what's happened in science over the last 100 years. The discovery of radioactivity and its first explanation, which many of you are familiar with from your college days and your education in physics, when in 1902 Rutherford and Soddy explained radioactivity, there was a debate about what this might actually mean. And in 1903, Frederick Soddy gave a lecture in which he warned that if, as he put it, the man who put his hand on the lever of atomic energy, in other words, to be able to control the process whereby nuclear energy is actually released, would possess a weapon by which he could destroy the Earth if he chose. And so this was a very fearful prospect that very quickly came to some of the physicists about the scale of the energy release that might be involved, and the implications in a world of warring states. And so it was a combination of a scientific understanding and a judgment about the prevailing political structure in the world of nation states which choose to wage war against each other as one way to resolve their differences. It took 30 years before Leo Szilard thought of the nuclear chain reaction, a way in which one could actually anticipate a runaway process for the release of nuclear radiation. And for Szilard, what we understand today in terms of the nuclear fission chain reaction, which is illustrated in this schematic here, through the process of nuclear fission, where a neutron strikes a nucleus of uranium-235, causing it to break into two pieces and release two or more neutrons, which then, if there is sufficient uranium-235 close by, will actually cause some of those other nuclei to also fission and release additional neutrons. And so you get a runaway fission chain reaction, which produces, each fission produces 100 million times the energy of the kind of chemical reaction that is the source of conventional explosives. And this process happens at a very rapid rate, with 80 doublings of the neutron population in a microsecond. So this process of the nuclear fission chain reaction produces very large release of energy in a very short period of time, which is basically the definition of an explosion. And so Szilard, when he had this idea of the nuclear chain reaction, history relates that he was actually in London crossing the street at a traffic light. And the fact that we can date it so precisely tells you something about the significance of this moment in the history of humankind. Szilard understood that the fission chain reaction, as he wrote, could liberate energy on an industrial scale from the atomic nucleus, but also construct atomic bombs. And so here we see this ambivalence between the peaceful uses of nuclear energy for producing electricity and other uses, and the use of the same underlying physics for the construction of atomic weapons, what we would call nuclear weapons now. And again, Szilard embedded his understanding of the situation in a political judgment when he wrote that there was very little doubt in my mind that the world was headed for grief. And this had to do with the state of international politics at that time, which was very soon we were to see the outbreak of World War II. And during World War II, physicists first began to think about how to turn the fission chain reaction into a bomb. And two refugee physicists who had fled Europe and ended up in Britain, Otto Frisch and Rudolf Perls, wrote a secret memo to the British government in March of 1940. So 7 years after Szilard has the first idea of the possibility of a fission chain reaction, we have a memo on the construction of what they called a super bomb. And they deduced purely from physics, and it's worth doing the calculations if you set your mind to it, that a nuclear fission chain reaction would be possible in uranium-235. And it's possible then to calculate, knowing the physics of the chain reaction, that the energy from a 5-kilogram bomb, as they calculated, would be equivalent to several thousand tons of dynamite. And so here we see the enormous shift in scale of the orders of magnitude that several thousand tons of conventional explosive would be equivalent to a few kilograms of a fission explosive yield. And when you imagine the destructive effect of this kind of explosive energy, it's easy to show that the blast would destroy most structures and therefore presumably life in a wide area. You can calculate the blast and the distance to which it would extend. And then they showed that no reasonable material or structure that was available at that time could be expected to resist this explosion. And because it's fission, when the uranium-235 nucleus is caused to disintegrate by the neutron, some of the fission products, in and of themselves are radioactive and go further decay. But then there is the fission products themselves, as well as the neutrons and other radiation that is released. And so they understood that this would be dangerous to human beings. They also understood that because of the effects of the fission chain reaction, these radioactive materials that would be released by the explosion would be transportable by the wind. And that therefore there would be an arbitrary quality to the way in which these radioactive materials would be distributed after the explosion. And they concluded their memo by saying that this bomb could probably not be used without killing large numbers of civilians. And so here you have from the basis of a purely theoretical physics analysis, an explanation and a very accurate deduction of exactly what it would take to make a nuclear weapon and what it would do. And with this memo, the British government then launched its secret nuclear weapons program, knowing full well, as the physicists told them, that you probably couldn't use this bomb without killing large numbers of civilians. Now, there was an effort by some physicists at that time to try and help policymakers understand the danger that nuclear weapons would pose to the world. So in 1944, with World War II still raging, Niels Bohr, who all of you will have read about as the founder of our modern idea of the structure of the atom, actually took a very active role in trying to explain the dangers of the coming age of nuclear weapons to the most senior policymakers that he could gain access to. So he actually wrote to and met with the President of the United States and to the Prime Minister of Britain and others, and he urged them to talk to the Soviet Union about nuclear weapons. At that time, the Soviet Union, the United States, and Britain were all allies in the war against Nazi Germany. But the secret British nuclear weapons program, which then became the secret American nuclear weapons program, was kept a secret from the Soviet Union, even though the Soviets were allies. And Bohr worried that by keeping it a secret, there would be the risk then of an arms race after the war between the Soviet Union and the Western powers. In part because the atomic bomb that was under development by the United States, with help from Britain and others, was, as he put it, a weapon of power far beyond any previous possibilities. And his advice was rejected by both the US government and by the British government. They wanted to keep it a secret. They wanted to keep the bomb to themselves. Some of the scientists who actually worked on the nuclear weapons program in the United States, including Leo Szilard, who a decade earlier had thought of the nuclear chain reaction, actually petitioned the President of the United States, asking them to think about the consequences of nuclear weapons. And they warned that the nuclear weapon that was now almost completed by the United States was only the beginning of what nuclear weapons might become. That it was only the first step in this direction once we learned to make nuclear weapons. He says there is almost no limit to the destructive power which will become available in the course of their future development. So the atomic bomb that was under construction was not the end, but the beginning of the evolution of ever more powerful and destructive weapons. And he warned very clearly that the cities of the United States, as well as the cities of other nations, would be in continuous danger of sudden annihilation. So they petitioned the president, first of all, don't use the nuclear weapon arbitrarily. Secondly, think about the consequences of using it and keeping it a secret and trying to use it for military or political advantage. And again, as with Niels Bohr, Szilard's advice was rejected. This is where the gap between the physicists and the policymakers becomes the most stark. And this is not a history lecture, so don't worry. But if we are to date the point at which one could imagine a different path that the nuclear age could have taken, it's April the 25th, 1945, between noon and 12:45. And we can date this so precisely because we have the diary records of the people concerned. So President Roosevelt, who was the President of the United States, passed away, and he was replaced by his Vice President, Harry Truman. Truman, even though he was Vice President of the United States, had not been told about the secret Manhattan Project to build the atomic bomb. Congress also was not told about the secret project to build the atomic bomb. So Truman becomes president, and he is given his first briefing about the secret bomb program by what was then the Secretary of War, what we now call the Secretary of Defense, and Henry Stimson. Stimson left behind his memo and his diary in which he explained this. I went to see the president and this is what I told him. And so Stimson told President Truman in this conversation that we are building and have almost finished the most terrible weapon ever known in human history. These are Stimson's words to the president. And that the world would eventually be at the mercy of such a weapon. Modern civilization might be completely destroyed. I mean, you can imagine what it must have been like for Truman to hear such a stark description of the military capacity the United States was about to achieve. At which point, Truman could have said, we need to stop this. Because you have to remember, World War II is almost over at this stage. And that there would be no justification for having a weapon like this. Truman decided to continue with the nuclear weapons program, and the first nuclear weapon test was carried out soon afterwards. The nuclear test explosion was in July of 1945. It was actually in New Mexico. Many people don't remember that. They think of nuclear weapons and they think of Hiroshima and Nagasaki, and I'll come to those in a minute. But the first ever nuclear explosion was actually on US territory. And the first victims of nuclear weapons actually turned out to be Americans. It was 21,000 tons of explosive power. And with nuclear weapons, it's not just the explosive blast, which is the kind of thing that you get from a normal explosion. There's also about a third of the energy is released as heat, and a small fraction in terms of the actual, what we would call nuclear radiation. And the most recent assessment, which is by the US National Cancer Institute, has found that as many as 1,000 cancers have already occurred or are projected from the radiation exposure to the residents of New Mexico at that time, because the nuclear test was kept a secret from the people in the area where the test was carried out because of national security. And there is actually now a campaign by the descendants of those communities in New Mexico for recognition and compensation for the sickness and suffering that was caused by that first explosion. So the US then took its test object, which was called the Gadget, and turned it into actual deliverable bombs to be dropped from airplanes on Japan. There were two types, one made from highly enriched uranium and one made from plutonium. Plutonium was a new element produced during the Manhattan Project for weapons purposes. And these were enormous weapons. You know, one bomb could only be carried by one airplane. And in both cases, in the use of one bomb was dropped on the Japanese city of Hiroshima, one was dropped on the Japanese city of Nagasaki. And there is, one has to admit, a certain cruel experimental quality to this decision to drop one bomb on one city and a bomb of the other type on the other city to see what they would do. In both cases, about 1 kilogram of material actually underwent fission. And the yields were, you know, of the tens of kilotons range. And so these pictures show what happened in the case of Hiroshima. Between 70,000 and 140,000 people were killed, almost all of them civilian. And in Nagasaki, between 40,000 and 70,000 people were killed, again, almost all of them civilian. The entire cities were basically reduced to rubble and burnt down to the ground, except for the strongest, most modern reinforced concrete and steel buildings. What became clear was that the nuclear weapon, the atomic bomb as it then was basically one bomb would kill a city. Whereas previously, to burn a city down to the ground took air raids of hundreds of airplanes, dropping thousands of bombs over a long period of time to do similar damage. And so this was an incredible increase in the efficiency for the destruction of cities. So with the end of World War II, and the physicists went home, many of them, there was a recognition that what we have done here is potentially of grave concern, and people need to understand. And so Albert Einstein, who was then at Princeton, helped found, along with Leo Szilard and others, the Emergency Committee of the Atomic Scientists. And the fact that they called themselves the Emergency Committee gives you a sense of what it is that they felt was the scale of the peril. And Einstein wrote a letter to physicists all over the world asking for money. to begin a campaign to educate the world about the danger of nuclear weapons and the need for their elimination. And in his letter, Einstein basically crafted what you can see as a manifesto for what he imagined of the role of the physicist as a citizen scientist, where a physicist combines their obligations as a citizen in a democratic society with their technical knowledge, where he says, we scientists recognize our inescapable responsibility to carry to our fellow citizens an understanding of the simple facts of atomic energy and its implications. We believe that an informed citizenry will act for life and not for death. In other words, if you tell people the honest, scientifically accurate facts about what nuclear weapons are and what they do, then hopefully they will choose a path to reduce and end the nuclear danger. And this was not just a quixotic quest by physicists, but it was also something that the international community struggled to try and put in place. At the same time as Einstein is writing his letter, the United Nations is being created. And with the rubble of World War II, the destruction of large numbers of cities in Europe and in Japan, the devastation of large areas of the world and millions of refugees, the United Nations was set up, as it says in its charter, with the goal to free humanity from the scourge of war. And so when the United Nations had its very first meeting in January of 1946, the first decision they made was to create a commission to deal with the problem raised by the discovery of atomic energy. This is before deciding on what to do about helping rebuild the world after the devastation of World War II, before even deciding what are the official languages of the United Nations. The first thing the United Nations took up was, we need to have a plan to eliminate atomic weapons and all other weapons adaptable to mass destruction, as they put it. And this is the oldest unfinished business of the United Nations. The plan was never developed. Instead, we got the Cold War between the United States and the Soviet Union, exactly as Niels Bohr had warned. The Soviet Union saw the United States use atomic weapons against Japan, worried about the future conflict between capitalism and communism, between the West and the Soviets, and decided they had to have this weapon too. And so there was a crash program. And so in 1949, the Soviet Union tested its first atomic bomb, which relied in part on espionage, on spying on the Manhattan Project. But the first Soviet atomic bomb looked very much like the first American atomic bomb. And when the Soviets tested that first atomic bomb, the US faced a second fateful decision. The US government asked its scientists, who were organized into the General Advisory Committee, on whether they should build even more powerful thermonuclear weapons, fusion-based weapons, instead of fission-based weapons. And many of the scientists who were involved in the Manhattan Project to build the atomic bomb were members of this General Advisory Committee. So they were asked, could we build it and should we build it? And the scientists said, yes, we could build it, but we should not build it. And they said in their report, which was classified for a long time, that the reason for developing such super bombs, thermonuclear weapons, would be to have the capacity to devastate a vast area with a single bomb. Its use would involve a decision to slaughter a vast number of civilians. A super bomb, a thermonuclear weapon, would become a weapon of genocide. Its use would carry further than the atomic bomb itself the policy of exterminating civilian populations. In other words, this is a bomb for making genocidal war on civilian populations. The US government rejected the advice of the scientists about whether they should build the atomic bomb, and it said, just build it. And some scientists went ahead and built it. And the first US thermonuclear test was carried out a few years later. And it was vastly more powerful, as was to be expected, than the atomic bombs that had been developed during the Manhattan Project and used against Hiroshima and Nagasaki. And this photo here in the background of the slide shows that first thermonuclear test. And the mushroom cloud that we associate with nuclear weapons, it was 30 miles high and 100 miles wide. It was colossal. So again, the physicists tried to help warn the world about the dangers of these new super weapons. And again, Einstein played a pivotal role in trying to help this process. And in one of the last acts of his life, Einstein signed the Russell-Einstein Manifesto of 1955. People think of Einstein, especially, as a famous physicist, the general theory of relativity, special relativity, and for those who know their history, his work on Brownian motion, the photoelectric effect, and so on. But Einstein was not just a physicist and a mathematician and a philosopher. He was also an avowed socialist and a publicly declared pacifist. And he made no effort to hide his political views. And so together with the British mathematician and philosopher Bertrand Russell, they wrote this public statement in 1955, calling on scientists all over the world that, because of the danger of thermonuclear weapons, that it could possibly put an end to the human race. And they talked about the possibility of universal death, right? Sudden death for a minority who would die immediately in the war, but for the majority of humankind, a slow torture of disease and disintegration because of the collapse of civilization and the effects of fallout. So they said, we have to learn to think in a new way, remember your humanity and forget the rest. And this led to the founding of an organization called Pugwash, which brings together scientists from all over the world to try and help find an answer to the danger of nuclear weapons. And they played an important role during the Cold War by bringing scientists from the West and scientists from the Soviet Union together to try and find ways of reducing the danger of nuclear weapons. And they won the Nobel Peace Prize in 1955. But it didn't matter to policymakers that scientists were arguing and explaining this danger. The military and the policymaking process, saw the possibility of these weapons. And so we can now see, because of US laws about the declassification of information, and an amazing memoir that was just recently published by Daniel Ellsberg called The Doomsday Machine, Confessions of a Nuclear War Planner. Ellsberg was a civilian expert who worked in the White House for President Kennedy. And one of the things that he did was to draft a letter for President Kennedy to send to the US military leadership, asking how many people would die if the US carried out its nuclear war plan. Up to that point, no one had ever asked this question before. So Ellsberg in his memoir explains how he wrote this question and how President Kennedy signed it, and it was sent to the military, and immediately the answer came back in this chart, which is, as it says, top secret, sensitive, Joint Chiefs of Staff, which is the military leadership, for the president's eyes only. They knew the answer. They didn't have to work it out. They'd already worked it out. And the answer was that the US nuclear war plan in 1961 was expected to cause 325 million deaths within 6 months. But that was only deaths with regard to Russia, to the Soviet Union. The question then went back, what about other people who would die? And the answer came back, there would be another 100 million deaths in Eastern Europe, 100 million deaths in Western Europe, 100 million deaths in states also adjacent to the Soviet Union and China, and that the total expected short-term deaths from the US nuclear war plan in 1965 was anticipated to be 600 million people. They did not include people in the US that would die when the Soviet Union fired their nuclear weapons back at the United States. 600 million people is 100 Holocausts. And this was what the military planners intended and knew their war plan would do. So with that, let me stop and pause for a minute and ask if there are any questions, because I'm now going to move to the second part of my talk, which is about where we are now in terms of nuclear weapons and the nuclear danger.
I have a question. Is it okay just to ask?
Please.
Yeah.
Yeah, my question was, I was wondering about the difference size-wise between conventional nuclear weapons and thermonuclear weapons, you know, the ones that we talked about, being the nuclear weapons being around the kiloton range, but the thermonuclear weapons being the megaton range. What's the physical size difference between the two?
Okay, so that's a great question, and this slide will answer it, and I will use this as a transition. So the picture here on the left shows the first atomic bomb, the one that was tested in July of 1945. And for the scale, you can see the two people standing next to it. So this was the plutonium fission weapon, 21 kilotons, 21,000 tons of conventional explosive equivalent. And this is basically what was put into a shell and put onto the airplane and used to destroy the city of Nagasaki, plutonium-based fission weapon. On the right, you see a modern American W-80 cruise missile warhead, which is a two-stage thermonuclear warhead, which has a yield that can be varied. You can set it for 5 kilotons or 150 kilotons. And warheads that are of the 1 megaton range, which the US no longer has in its arsenal anymore, except for one, are not much larger. So that's the scale. So a modern fission weapon, which the US really doesn't have in its arsenal anymore, all US weapons are now thermonuclear weapons, because they've learned how to produce weapons where you can vary the yield from the yield of equivalent to the yield of a fission weapon up to the yield of the hundreds of kilotons. And most weapons in the US arsenal now are of the order of several hundred kilotons. Are there more questions?
Yes, can you go back to 2 slides?
Sure, ask your question.
Oh yeah, I think I just want to clarify these things a little bit. I think like the 600 million, that is actually underestimated in these days, because we have a lot of more people and higher density in these days comparing to like 1960s. So I just want to emphasize, it's maybe even better just to quote the percentage of the people on the earth will be eliminated by the nuclear weapon.
Yeah, you're quite right.
More shocking.
You're quite right. But you have to remember that the nuclear arsenals were also very different in terms of the number of nuclear weapons and the number of targets that they would be aimed at. In 1961, as you can see here, the US had of the order of almost 25,000 nuclear weapons. The US stockpile is given here in the blue line. And whereas the US arsenal now is much smaller. And so the war plan, which is the combination of what weapons you have and what you intend to attack with those weapons, along with, as you quite rightly point out, the actual number of people, has an effect on the estimated casualties. But there are other factors that also come into play, which we now understand, which they did not understand back in 1961 about effects of nuclear weapons, which I'm going to explain in a second, but you're quite right. So let me just press on then for a second. So if you look at the evolution of the global nuclear stockpiles from 1945 up to now, you can see that the US arsenal peaked at over 30,000 nuclear weapons in the late 1960s. And the Soviet Union was struggling to catch up, and the Soviet Union's stockpile is shown in red. And they eventually crossed in the late 1970s, and then around the time of the end of the Cold War, both stockpiles started to reduce significantly. The total peak, as best we know it, of nuclear weapons was about 70,000 nuclear weapons in 1986. And just for comparison, you can see that I mean, there are currently 9 countries with nuclear weapons, and the US and Russian stockpiles are shown here in the red and the blue curve, and all the other 7 countries' nuclear weapons are shown along the bottom. They barely are visible above the axis there because their arsenals are so small in comparison to the extraordinary arsenals that were built in the Cold War. And one other feature worth mentioning here is that if you look to where we are today, 2020, 2021, the deployed arsenals, which are the yellow, the blue and the red lines here, are actually a fraction now of the total inventories because there are such large stocks of weapons that have been retired and are awaiting dismantlement. So to make possible such enormous modernization of nuclear weapons that I showed with the making them smaller and lighter and more destructive and have variable yield and other properties, it was an intensely experimental process. And so there have been more than 2,050 nuclear explosions as part of nuclear weapon testing and development programs at over 60 locations around the world. And if you look at the pattern of where they are, most of these nuclear tests have been done either in the colonies of power, so Britain and France tested in colonial territories, in Algeria and in the Pacific and in Australia. The US tested in the Pacific Islands and in the Nevada test site, which is the home of the Western Shoshone Nation. And in poor communities in many areas, the Soviet Union had its test site, but that's also true of India and Pakistan and China in terms of where they tested nuclear weapons. In part because these are areas where population densities are low and the people that live there are not considered to be as important or as politically significant in the decision-making process. And of the 2,050 or so nuclear explosions, more than half were conducted by the United States. And the most bombed place on Earth is Nevada. There were 928 nuclear explosions there between 1951 and 1992. We know, as the scientists warned back in 1940, about atmospheric fallout from testing that is done above ground. And Andrei Sakharov, the Soviet physicist who helped build Soviet thermonuclear weapons, actually estimated the health effects of just the carbon-14 from the fallout caused by atmospheric nuclear testing, and estimated that 1 megaton worth of nuclear yield from thermonuclear weapons would cause cancer in about 10,000 people. And if you do the modern version of that calculation, it was more or less right. And so if you just do the arithmetic, then there has been 545 million tons of thermonuclear testing by the US, the Soviet Union, Britain, France, and China. Everybody else tested their nuclear weapons underground, except for the possibility of one test by Israel. And you can just work out what 545 megatons of testing does by using Sakharov's criteria. And the US National Cancer Institute actually has studied the effects of atmospheric fallout from US testing in Nevada on the US continental population. And they estimated about 20,000 extra cancers and about 6,000 deaths in the US population from US testing of US weapons at the Nevada test site. And this map actually shows the radiation dose to the thyroid per person from US nuclear weapon tests across the United States. And you can see patterns of fallout which are shaped by wind and cloud and rain and so on, with these hotspots that show up in quite faraway places. And it's actually worth, if you're interested, you can actually go to the National Cancer Institute study and actually see what the estimated dose is that your county would have got back then. So in terms of what it took to build those vast nuclear arsenals, the 70,000 nuclear weapons that I mentioned, there were enormous efforts at the production of fissile materials. The highly enriched uranium and the plutonium that drive the fission chain reaction that make nuclear weapons possible. And so one of the things that we do at Princeton as part of our work is to try and understand the past production of these nuclear materials and to estimate global stockpiles of these materials today, and to think about what are the options for eliminating these materials as the number of nuclear weapons declines and eventually goes to zero. And so our best estimate is that there's about 1,860 tons of plutonium and highly enriched uranium in the world. And not all of it is in weapons. Some of it is in weapons. Some of it is in weapons that are waiting to be disassembled. Some of it is in material that is from disassembled weapons. And some of it is in other applications or just in storage. But if you take it all together, it's enough for about 240,000 simple nuclear weapons. And about 99% of this is held by the 9 nuclear weapon states, mostly by Russia and the United States. It's legacy of the giant arsenals of the Cold War. The good news here is that the US, the UK, Russia, France, and China have all stopped producing material for weapons because they have so much of it. But production does continue, as best we understand it, in Israel, India, Pakistan, and North Korea. So where are we today? And I'm getting to the end. We have 1,800 US, Russian, British, and French weapons ready to fire within minutes out of a total stockpile that exists today. And here are the kind of national estimated stockpiles. We know what it is exactly for the US because the US has publicly declared how many nuclear weapons it has. The US also has a posture that it will be the first. It is prepared to be the first to use nuclear weapons in a conflict, should it decide to do so. Some countries have adopted a policy of no first use, that they will not start a nuclear war, but that they are open to retaliation if they're attacked by nuclear weapons. And nuclear weapons today are found on land-based and sea-based ballistic and cruise missiles, and on nuclear-armed bombers and fighter planes. So lots of accidents happen involving nuclear weapons, including in the US and elsewhere. Weapons have fallen off airplanes. Weapons have exploded in silos. Weapons have been mistakenly loaded onto bombers and flown across the country without people realizing that that airplane was carrying nuclear missiles. This was in 2007. And now we actually are starting to see incidences of where the command structure in the US, for example, about which we know the most, actually had lost contact with 15 nuclear missiles for an hour. So the US itself has reported 32 serious nuclear weapon accidents in a period of 30 years. So you can estimate the frequency of nuclear weapon accidents. There also have been many false alarms of nuclear attacks where the US military and political leadership has feared that the US may be coming under nuclear attack. So over a period of decades, there have been instances where the US system of satellites and radars has mistakenly seen signs of incoming Soviet and Russian missiles, caused by things like the moon or defective computer chips. And the Soviets they saw in the past their own problems where their satellites saw US missiles coming towards them. And the most recent significant case was in 1995, where a Russian radar detected what it thought was a US missile launch directed at Russia, but it was actually a scientific experiment involving a rocket. And now there is great concern that as nuclear command and control systems move to increased reliance on advanced information technologies, that there is the risk of cyber attack and hacking and other kinds of things that may cause false alarm of nuclear attacks. So it's not that all these nuclear weapons sit safely in one place and we're not at risk of things happening. I mentioned earlier that one of the things that they did not understand in 1961 when they made their estimate of how many hundreds of millions of people would die from a nuclear war was that modern thermonuclear weapons of the size that is, prevalent in the arsenals of the US and other nuclear weapon states, most other nuclear weapon states, is the large-scale effect of fire. That this fire effect is actually much larger than the effect of blast. And it's been discovered that in the US nuclear war planning process, US nuclear war planners include the effect of blast, but not of fire, when they estimate the effects of the weapons that they use in terms of deciding what weapon to use on what target and how much damage that was caused. And this graphic shows the difference in scale between the area that would be destroyed just by the blast effect. In other words, it would be included in the US nuclear war planning effect, and the area that would be destroyed by fire, which is much larger, but is excluded from the nuclear war calculation. And there's a very important book by Lynn Eden called Whole World on Fire that explains why it is and how it came to be that US nuclear war planners chose to neglect the effect of fire. But what that means is that the number of people who would die would be much larger than that what you would imagine just from including the effect of blast. But fire does something else as well. Fire produces smoke and soot, which goes into the atmosphere. And so one of the things that scientists beginning in the 1980s realized was what has come to be known as nuclear winter, that the smoke and soot from burning cities set ablaze by thermonuclear weapons would cause potentially vast amounts of smoke into the atmosphere, which would linger, blocking out sunlight, and the reduction in light reaching the surface of the Earth would reduce surface temperatures, so it would become dark and cold, with catastrophic consequences for ecosystems, including agriculture. So those early models from the 1980s by people like Carl Sagan and others have now been re-understood and remodeled using modern climate change codes. And this is work that Alan Robock and his collaborators have been doing. And so they've shown that the scale of fire from even low-yield nuclear weapons on large cities, and they looked at South Asia, that the use of 50 weapons by India and 50 weapons by Pakistan could produce enough smoke and soot that it would actually darken most of the Earth's surface for about 25 years. And this simulation shows the pattern of smoke over a period of time, over the first couple of months. And they estimate that between the effects of the loss of light, the impact of darkness, cold, and ozone over this 2.5 decades, you would cause catastrophic global famine. And the citation for that work is given on this slide, and you can see it. And just this year, the US Congress has asked the US National Academy of Sciences to conduct its study on this effect, on the effects of the environmental effects of large-scale nuclear war. So let me just jump ahead now. The last thing is that we're at a time of great flux in terms of the efforts to control the danger of nuclear weapons. Throughout the Cold War, there was an effort, as I mentioned, led by the scientists originally, to get policymakers to understand the need for restraint, control, reduction, and elimination of nuclear dangers and nuclear weapons. And so a series of international and bilateral agreements were signed between the United States and the Soviet Union, and then in some cases with other countries also, to limit nuclear weapon systems and nuclear weapons and arms racing dynamics. Over the last 2 decades, there's been a systematic process by the United States of withdrawing from some of these treaties. So the Anti-Ballistic Missile Treaty that was signed in 1972, the US withdrew in 2002. The US became the first country ever to withdraw from a nuclear arms control treaty with that decision. The Intermediate Range Nuclear Forces Treaty that was signed in 1987, eliminating medium-range nuclear weapons held by the United States and the Soviet Union, and it reduced nuclear stockpiles by thousands of nuclear weapons. The US withdrew in 2019 following a decision by the Trump administration. Some treaties, like the Comprehensive Test Ban Treaty that bans the testing of nuclear weapons, the US signed in 1996, but has still not been ratified by the US Senate. And even recent treaties like the Iran nuclear deal that was signed in 2014, the Trump administration withdrew in 2018. So the idea of an enduring commitment to a process of the elimination of nuclear weapons in a step-by-step process has been put into doubt now, because what was previously imagined to be a ratchet effect, where each treaty binds and stabilizes the international situation, and then we move to the next step and add another layer of restraint, and then another layer of restraint, and slowly over time, but it seemed to be a one-way street. Over the last 2 decades, we've seen that that was a mistaken understanding, and that policymakers are, under certain circumstances, willing to undo those systems of restraint and reopen arms races. The most recent development has been that the New START treaty that was signed by the United States and Russia in 2010 was due to expire next week. Well, actually this week, on February the 5th. And it was only on the 29th of February that the US and Russia agreed to extend it for 5 years. And this was a decision the Biden administration took. The Trump administration had not been willing to commit to a renewal. The other thing, however, is that the politics of all of this has become very polarized. In 2020, during the Trump administration, the White House considered the resumption of nuclear weapon testing by the United States. And it was debated in the Congress during the budget process. And in the Senate, money was set aside for the US to prepare a nuclear test. In the House of Representatives, the vote was along party lines to not fund the test. Democrats voted to not fund a test. Republicans, by and large, voted to fund a nuclear test. And eventually, in the process of trying to get the House of Representatives and the Senate versions of the budget to converge, it was eventually decided to not fund a test. But the fact that the two political parties now have opposing views on nuclear testing raises the question about how long we can keep the moratorium on nuclear tests, which has been in place now for almost 3 decades, into the future. The last thing that's happening is that there has been an enormous commitment by the United States and the other nuclear weapon states to modernize their nuclear weapons and prepare for the next nuclear age. We're now 75 years into the age of nuclear weapons, and nuclear weapon systems have lifetimes measured in decades. And so it takes a long time to build and deploy these weapons. And once they are deployed, they last a long time. And so decisions are being made now in the US to spend $1.5 trillion over the next 30 years on new nuclear warheads, new missiles, planes, and submarines to carry those nuclear warheads. And these will be in service until 2070 and 2080 and beyond. The budgets that are being imagined, some of that money is already being committed. $13.3 billion was just authorized for the engineering and development of new missiles. And $8.5 billion has been set aside for a new nuclear submarine. Each subsequent submarine will cost similar amounts. And the current estimate is that it will take $15 to $20 million to make each new nuclear warhead that the US plans. And that's assuming that we just replace what we have and don't make more of what there are. And this just shows spending on just the nuclear warhead part itself. The US is now spending about 3 times as much per year on the production, R&D, and maintenance of nuclear weapons in constant dollars. So that's adjusted for inflation compared to the Cold War average. So we are in the middle of a major financial commitment to a new generation of weapons and weapons capabilities. So I will conclude with this. On the 22nd of January, the United Nations Treaty on the Prohibition of Nuclear Weapons entered into force. It's supported by 122 countries, and it says that countries cannot develop, test, produce, manufacture, acquire, or possess nuclear weapons, or use or threaten to use nuclear weapons. This treaty makes it illegal under international law to practice nuclear deterrence, that you will use the threat of nuclear weapons to defend your country. And it says that countries that sign the treaty must remove and destroy their nuclear weapons and eliminate their nuclear weapon programs. So we see a divergence now between 9 nuclear-armed states who are trying to modernize their nuclear weapons for decades to come, and the majority of the world's countries, which have now committed themselves through the international system to a legally binding prohibition of nuclear weapons. And it will be the tension between the power and politics of the nuclear-armed states on one side and the power and politics of the international community on the other side that will develop how all of this plays out. And where is the US public in this? The most recent polling suggests that a majority of the American public actually supports a nuclear weapon-free world, and has done now for quite a long time. Polls 10 years ago and 15 years ago found similar answers that on average, 60% or more of the US public actually believes that no country should have nuclear weapons. And so we then see not just a split between nuclear weapon states and non-weapon states, but also a split between publics and governments on this issue, with governments committing to nuclear weapons and modernization, and the publics seeking a world without nuclear weapons. And this is where I'll just end with this slide about the Physicists Coalition for Nuclear Threat Reduction. And we're trying to bring this message that we are at a pivotal moment in thinking about the future of nuclear weapons. And we need to begin to find ways to engage the public and the Congress and the policy process in the US and eventually around the world on how to make sure that we don't get ourselves into a new nuclear age with continued risk of nuclear weapons, and to find ways to end the nuclear threat. So with that, I will stop, and I welcome your questions.
Thank you very much for this very interesting talk. I'm sure there are questions.